In this video, we're going to be finding the standard matrix for the clockwise rotation transformation for vectors in R2. So let's say we had this vector v in the xy plane and we wanted to rotate it clockwise an angle theta, and it ends up at this as this new vector v sub c. We want to find out the matrix a sub c of theta. Well, this should be a sub cc, but here we want to find the matrix a sub c of theta, that if we left multiply v by that matrix, then we end up with this new vector v sub c. So in this video, we're going to be figuring out what this matrix a sub c is. In a previous video, we found the standard matrix for the counterclockwise rotation transformation. So we start out with this vector v and we rotate counterclockwise an angle theta. We end up with a new vector v sub cc. And the standard matrix for that transformation is this matrix here. So cosine theta, sine theta in the first column, and negative sine theta, cosine theta in the second column. But we want to find the corresponding matrix for the clockwise rotation transformation. So here is how we do it. So we can call this matrix a sub c, as shown here, of theta equal to, well, if you recall, rotating an angle theta clockwise is equivalent to rotating an angle negative theta counterclockwise. So we can actually just plug in negative theta for wherever we have theta in this counterclockwise rotation matrix. So instead of cosine of theta in row 1, column 1, we can enter cosine of negative theta. Instead of sine of theta, we can enter sine of negative theta. Same thing here. Instead of negative sine of theta, we have negative sine of negative theta. And here, instead of cosine of theta, we have cosine of negative theta. Okay, hopefully you remember your odd-even trig identities. Trig is cosine is an even function, so cosine of negative theta is equal to cosine of theta. Sine is an odd function, so sine of negative theta equals negative sine of theta. Again, sine is an odd function. Sine of negative theta is negative sine of theta, but we have another negative sign in front of that, so this is positive sine of theta. Cosine is an even function. We have cosine of negative theta. That's equal to cosine of theta. So here is our matrix for this clockwise rotation transformation. So let's say hypothetically we had the vector 1, 2. Say this is the y-axis, this is the x-axis, and we'll say this is the vector v 1, 2, and we wanted to rotate this. I don't know. Let's say we'll just keep it abstract or heck, we can make it more concrete. We wanted to rotate this pi over 2 clockwise. So say it ends up here. So I'll call this v sub c, and we want to figure out what we want to figure out what particular where this vector actually ends up, what this v sub c is. So all we have to do is we can write, well, v sub c is equal to a sub c of pi over 2 times v. So a sub c of pi over 2, well, that's going to be cosine of pi over 2 times minus sine of pi over 2 times sine of pi over 2 times cosine, or not times, I didn't mean times. So this entry is minus sine of pi over 2. This entry here is sine of pi over 2. And this is just plugging in pi over 2 for theta in this matrix above. And this entry is cosine of pi over 2. And of course, this is going to be multiplied by the vector 1, 2. So this would be 0, 1, negative 1, 0, times 1, 2. And it's the same thing but as saying entry 1 times the vector 0, negative 1, plus the entry 2 times the vector 1, 0. And that'll just give us 0, negative 1, plus 2, 0. And we end up with the vector, adding the corresponding entries, we end up with the vector 2, negative 1. So I guess it would end up roughly here. So hopefully that gives you some insight into how we can use this counterclockwise rotation matrix to derive the clockwise rotation matrix, and in turn use that to figure out where vectors rotated a certain angle clockwise will end up.